All right. So, as someone pointed out, this is section 5.3, not 3.3. In the previous version of the book, this was chapter 3. We kind of talked in general about extrema very, very, very vaguely. We're going to talk more specifically about it today, and we'll get even more specific later. But remember that if f prime is positive on an interval, then f is increasing on that interval. And if f prime is negative on an interval, then f is decreasing on that interval. So we have what's called the first derivative test for local extrema. And you've already kind of been doing this on last night's assignment. Let c be a critical number of a function f, which is continuous on an interval containing c and differentiable on the interval except possibly at c. We probably ought to talk about what a critical number is. A critical number is if f prime of c is equal to 0, or f of c exists, but f prime of c does not, c is a critical number of f. Okay, and critical on this is not in the sense of something that's frequently critical is if someone's in critical condition, that's typically bad, right? But what it means more generally, something is critical if it can turn either direction, right? It's like a tipping point. You see this in sports all the time. They'll be like, this is a critical fourth down, right? Meaning it could go either way. Okay, and that's the sense of critical number here. When you have a critical value, the function could, if it's increasing, suddenly turn around and go the other direction. But it doesn't have to. It could continue going the same direction. Or if you have a point where the derivative doesn't exist, you could have a change in direction, but you don't have to. Okay? So they are potential turning points. That's the way I like to think about them. Critical points are potential turning points. So if f prime changes from negative to positive at x equals c, f has a relative minimum at c f of c. And if f prime changes from positive to negative at x equals c, f has a relative maximum at c f of c. These used to be really, really, really common questions on the free response at the AP exam. Usually there's something that's going to ask you to do something like this on the free response. They're not as straightforward as they used to be. They used to be boringly straightforward. Now it's a little more nuanced, but this happens all the time. If you say f prime changes from negative to positive at x equals c, then f has a relative. That's how you justify things when you're asked to justify why is this a local maximum or why is this a local minimum. Relative minimum and local minimum, same thing. They just mean it's lower than everybody else around them. It's like when you're a little kid where somebody in your neighborhood was, I don't know, exceptionally strong or exceptionally fast or something, or in my case, exceptionally fat. Take your pick, right? Are they the fastest person in the world? No. Are they the fastest person on their block? Okay. That is a relative maximum. They are the fastest in their neighborhood. And actually, in math, they'll sometimes talk about it being in the neighborhood. Okay? And that's exactly what they mean. So, here, instead of being given the function f, frequently you will be given a graph of the derivative of f. Be really careful about what thing you're looking at. This wants the x-coordinate of each relative extrema of f, not of f prime. And this is the graph of f prime. All right, f prime has a local maximum here and a local minimum here and a local maximum here and a local minimum here. But that's not what they're asking. They're asking the relative extrema of f. Well, if we look at this, I'm going to divide this up here and here and here. Why am I dividing it up at those places? Because those are critical points of f, because f prime is equal to 0. Those are potential turning places. So in this region, f prime is positive, which tells you what about f? It's increasing. Then on this next interval, f prime is negative, which means that f is doing what? Decreasing. When f changes from increasing to decreasing, what do we have on the graph of f? Yeah, so f has a local maximum at x equals b. All right, on this next interval, is f prime positive or negative? Pardon? Negative. So f is still decreasing. Is there a local minimum or a local maximum there? No, there's no local extrema. This is you're in your car, you're backing up, you stop, and then you keep backing up. All right, you're moving in a negative direction, you stopped for a brief second, and then you continued backing up. Okay, no change in direction. Then here, f prime is positive, so f is increasing. So f has a local minimum at x equals f. One of the things that you have to be very careful of is not mixing up positive with increasing. When the derivative is positive, the function is increasing. All throughout this area, the derivative is positive. The derivative increases and then decreases, but the derivative is all above the x-axis, so it's all positive in there. That's one thing that almost everybody at some time, I can remember going through it, is you start mixing up increasing with positive. It all sort of runs together. You have to be very, vigilant is not the right word, but it's close, about keeping track of what it is you're actually saying. And in these, when you're giving a justification, try not to use the word it, because there are two different functions going on. Try not to use the function either, because there is the derivative, which is a function, and the original function, which is also a function. Okay? All right, let's move on. Page 2. Find the intervals on which f of x is equal to x cubed minus 3/2 x squared. is increasing or decreasing. All right, so we will start by taking the derivative to help us find critical points. That's 3x squared minus 3x. We want that to be equal to 0, so I'll factor out a 3x. So either 3x has to be equal to 0 or x minus 1 is equal to 0. Most common mistake on a problem like this is ignoring this first part. You're so used to looking in parentheses and going, oh yeah, because I factored this. Don't forget any variable out here. So either x is 0 or x is equal to 1. So I'll partition my number line like so. If I pick a number bigger than 1, say 2, don't get crazy with this, and substitute it into the derivative, 3x is positive, x minus 1 also positive. Multiply two positives together. We don't really care about the value, we just care that this is positive. If I pick a value between 0 and 1, say a half, 3 times a half is positive, half minus 1 is negative, f prime is negative. If I pick a negative value for x, 3x is negative, x minus 1 also negative, so f prime greater than 0. Which, before I go on and finish this problem, we should have known already. What kind of a graph is this going to have? Just what's its general shape? It's a parabola. Is it facing up or facing down? Facing up. F prime's got to look something like that. Sometimes it's faster and easier just to go, I don't need to check all those points. I know what this graph looks like. Okay, so f is increasing on the interval from negative infinity to 0, and again from 1 to infinity. And f is decreasing on the closed interval from 0 to 1. All right, let's move on. Find the x-coordinate of each local extrema. Okie dokie. So we'll take the derivative to find critical points. This will be 1/2 plus sine of x. We'll set that equal to 0 to find any critical points. So negative 1/2 is equal to sine of x. Let's see, that'll be at, it's going to be one of the pi over 6s. It'll be 7 pi over 6, and again at 11 pi over 6. This time we're only looking in between 0 and 2 pi. So let's say I pick pi in here. Sine of pi is 0 plus a half, so f prime positive here. And in the interest of time that we're starting to run out of, I'm just going to tell you that it does keep switching back and forth. So f has a local, will this be a local minimum or a local maximum at 7 pi over 6? Pardon? Nope. F prime's positive, then negative. Gotcha. So there's a local maximum at x equals 7 pi over 6. And f has a local minimum at x is equal to 11 pi over 6. Oh, it's just the one. Okay. It's like, I have a whole nother page. So here, again, same thing. We'll take the derivative to find critical points. So this would be 2/3 of x squared minus 9 to the negative 1/3 times, because of the chain rule, 2x. So I'll set that equal to 0. That'll be 4x over 3 times the cube root of x squared minus 9. Notice the original function, you can put anything you want to in this because we're taking the cube root. You can take the cube root of both positive numbers and negative numbers. So no problem there. However, for the derivative, we know the numerator's got to be 0. So x is 0. And f prime does not exist where? What x values make this derivative non-existent? Plus or minus 3. We get so focused on finding where the derivative is 0 sometimes, it's easy to forget to look to see, is there a place where the derivative is not defined but the function is defined? So we've got 3 critical points on this one. At 0 and at negative 3 and at positive 3. So there's one other thing to notice though. You're like, wait a minute, this seems odd. If I substitute in negative 1, I get into this. I'm taking the cube root. Oh, that'll work. I can take the cube root of a negative number, right? So if I put in negative 1, the numerator is going to be negative. The denominator is also going to be negative because I'm taking the cube root of a negative. So f prime greater than 0. If I substitute in positive 1, the numerator is now positive, but the denominator is still negative. F prime less than 0. If I pick a number larger than 3, numerator is positive, denominator is positive, so f prime greater than 0. And if I pick an x value less than negative 3, my numerator will be negative. My denominator will be positive, so f prime less than 0. So f has a local minimum at x equals negative 3 and at x is equal to positive 3. and f has a local maximum at x equals 0, where the derivative changed from positive to negative, which means the function changed from increasing to decreasing. Can we do this next problem in 2.5 minutes? Let's find out. Where does this function not exist? 0. Thinking about the domain is a good idea before you even start. Also, I can simplify this function to be x plus 1 over x cubed, or x plus x to the negative 3. That may be easier to take the derivative of. So f prime of x is going to be 1 minus 3x to the negative 4, not negative 2. Be careful about that. Set that equal to 0. So I'm going to move the 3 over x to the 4th to the other side. So that would mean 3 is equal to x to the 4th. So x is going to be plus or minus the 4th root of 3. So I have to keep 0 in here. Notice, does the derivative exist at 0? No, because I have this 0 to the negative 4th power. That puts it in the denominator. Now, the 4th root of 3, I don't know how big it is. I know it's bigger than 1, though. So I'm going to use 1 as a test point. That's going to be 1 minus 3. F prime's negative. Again, I don't know exactly how big this is, but I know it's less than 10. So substituting in 10, that's going to be 1 minus 3 over what? 10,000? So that's going to be positive. And the signs just alternate. Didn't quite make it. All right, y'all have a terrific weekend.